So now that we have a pretty good handle on the Diels-Alder, and we've looked at the issue of Diels-Alder stereochemistry, in this mini lecture we're going to look at regiochemistry. So let's get started. This is where we are. We know the Diels-Alder is kind of a no mechanism where a diene and a dienophile, as long as they have the right orbital configuration, they overlap in one swell FOUP. It's all about the orbitals and whether or not the reaction is symmetry allowed, and a 4+2 Diels-Alder concerted reaction is. Stereochemistry wise, it's retained. You can't be mucking around with rotating around single bonds or anything because it is a concerted reaction, and the relative stereochemistry of the diene and the dienophile is consistent, stays intact. So now we're going to look at regiochemistry and synthesis. The rest of the chapter is really focused on oxidations, so this will wrap up our Diels-Alder. So the nice thing about regiochemistry is that it really makes sense. So if we keep in mind the fact that the diene having two double bonds is the electron-rich HOMO, the donor, and the dienophile is the relatively speaking electron-poor acceptor, then it turns out that the substituents on these two pieces, substituents on the diene, substituents on the dienophile, will play a really important role in guiding regiochemistry. And the nicest thing of all, it's a great review of resonance. So here's an example of some kind of diene, remember our electron-rich piece, that has an electron donating group on it. And if you think about having an electron donating group on that second carbon in, well then it makes sense that there would be a resonance contributor here that would put a big old negative charge on that terminal carbon, making that terminal carbon quite electron-rich. So the hybrid would look like this, where the electron richness, the electron density, is going to be unequally distributed in the diene, and in fact it's really this guy who is the most electron rich. Now if we look at the dienophile, well, remember the dienophile should be electron poor, so we have, say, an electron withdrawing group on it. For example, we know that a carbonyl is electron withdrawing because we can draw this resonance contributor like so, just from pulling the pi electrons onto the more electronegative element, the oxygen. So clearly a carbonyl is electron withdrawing, but an even better resonance contributor is to show how we can pull the electron density all the way from this terminal carbon on the dienophile up onto the electronegative oxygen, so that the resonance hybrid for this guy shows that there's a bigger delta positive on this carbon than on that. So for both the diene and the dienophile, we've got an unsymmetrical, unequal distribution of charge, so that when we put them together, the charges are going to match up. For the diene, we see that basically the negative delta minus on the diene is going to match up with the delta positive on the dienophile. So basically we get regiochemical control on the basis of that unequal distribution of charge. And we get one regioisomer only, the one where the charges match up. We do not get any of the cyclohexene product, where the carbonyl would be flipped upside down. Okay, so this is not formed, only this is formed, and that is because the charges match up. Okay, so it is a one swell FOUP mechanism with no nucleophile, no electrophile, but this unequal distribution of charge does control the regiochemistry. So, a couple of examples. Now remember that it's a lot easier if you just redraw these things so that I can really clearly see my diene here. Now, we know that this is a delta positive because that guy is an electron withdrawing group. Now, a methyl group, is that electron donating or electron withdrawing? Well, we've always said that alkyl groups are electron donating. That's why, for example, a tertiary carbocation is more stable than a secondary, and in turn more stable than a primary. So that implies that this is electron donating, and if it's electron donating, that should push electron density all the way down to that terminal carbon. In which case, I've got to flip this around so that my diene looks like this, because I want my delta minus to match up with my delta plus to give me that regioisomer. And these regiochemical outcomes are pretty much exclusive. So if any of the other regioisomer is formed, it is definitely a minor product. How about the one below? Well, in this case, we definitely know that the lone pair on that oxygen is going to push electron density right there onto the terminal carbon. That means that's our delta minus. Here's our delta plus. Why is the NO2 group electron withdrawing? Well, Lewis structure time, the NO2 group is just about the most electron withdrawing substituent there is, because there's a formal charge of +1 on that nitrogen. So that's tremendously electron withdrawing. We can draw this resonance contributor. So it's positive charge on that terminal carbon, and then I've gotten a negative charge out onto the oxygen where it's relatively happy. So clean this up a little bit. What do we have? We have NO2. I'm just going to put an R here. So, doot, doot, doot. What do we end up with? The NO2 and the silyl ether completely opposite one another. So, that is how the regiochemistry of the Diels-Alder is controlled. In this particular reaction, this is a really nifty reaction because the fluoride anion is exceptionally good at reacting with silicon. And so it breaks the silicon-oxygen bond to give you this guy in just a plain old SN2 reaction plus Me3SiF. This is super strong silicon-fluorine bond, very, very strong. So that's the driving force. And of course, you should recognize that as an enolate, which rapidly tautomerizes to the ketone. So that's a pretty nifty way to make a ketone, a cyclohexanone. Alright, so your mission at this point, your goal is to think about this and think about, hey, for my electron-rich diene, what kind of electron-donating substituents can I come up with? And how does it change the regiochemistry when the electron donating group is on the second carbon versus the first carbon? Similarly, come up with a list of electron withdrawing substituents that would be on your dienophile and how does that impact regiochemistry? Now, before we sign off, let's take a quick look at synthesis, which for the Diels-Alder, the disconnection or the retrosynthetic step is super straightforward, because all you have to do is look at that double bond. You basically have to look at your cyclohexene. There it is. There's my double bond. And just do the retro Diels-Alder. I'm going to push that electron pair back. I'm going to break that bond and do just the retro mechanism for a Diels-Alder. And what does that give me? That gives me my diene and my dienophile. So just quick show those arrows again. Push that down. Always start at the cyclohexene. Push that up and push that over to create your diene, and there is the precursor, the one step backwards for making that molecule by a Diels-Alder. And of course, anytime you see a cyclohexene, you're going to think, oh, Diels-Alder for sure. Now, how about this one? It's a little bit trickier because it's a cyclohexadiene. So I've got two choices here. I could either start with this one, and I could do that, in which case I end up with this diene and this dienophile, or I could end up doing it, how about if we start with this guy, and it doesn't matter if I go clockwise or counterclockwise, that's totally immaterial. Boy, that's a mess. Basically, though, I'm making my diene on the other piece, and this is my dienophile. So up here we had this guy, and the bottom you can see they both in theory should make that same molecule, make that same Diels-Alder product, but which one is better? Well, in this case the one on top is definitely better because, as we're used to seeing, this is the electron rich diene, and it has the electron donating methoxy group on it. This has the electron poor electron withdrawing group on our dienophile. So this is the way the Diels-Alder works best. This is not as good because our diene is electron poor and our dienophile is electron rich, and those just don't work as well. So that's a wrap for the Diels-Alder. But in the meantime, did you hear about the woman who walked into a bar and she had her little pet up on her shoulder and said, I'd like a drink for myself. I think I'll have a Bloody Mary, and I'd like a beer for my pet Tiny. And the bartender looked at her and said, well, why do you call your pet Tiny? And she said, well, because he's minute. Get it? Minute? Yeah, these are getting worse, aren't they? Maybe I should take a vacation from these bad jokes. You'll have to let me know. Okay, next up, oxidations. See you in class.